Getting going with aliveness. Back in action. Hello again, friend. Welcome back for another session of Haskell hacking. My name's James, the Agent Ultra, and yeah, we're going to continue on building a database from scratch in Haskell just to muck around and learn something new. Excuse me. Today's a bit of a low energy day for me, but we're going to try and get through this. We're going to continue on, I guess, probably where we left off last week, working on data store. So our approach to this data store so far is to implement a B+ tree. And B+ trees are an interesting data structure. They come from needing indexes back in the day for speeding up disk accesses. When disk accesses were really expensive, they still really are. But you needed a way to kind of index into these blocks on the disk in a significant way, so you don't have to load every single block in the whole database. And so you created like a little table. And we created multi-level tables, right? So we had indexes on top of indexes that would load in parts of the index in chunks. And that's good. Multi-level indexes and M indexes are good. But they have a limitation that they can create degenerate trees if you're not careful. And there weren't any kind of strong rules about how to construct these multi-level indexes or M indexes or whatever you want to call them. So then B trees are invented. And B trees impose some of those rules on multi-level indexes so that we can construct them in a consistent way with some rules. Pardon me, I'm really itchy tonight. Excuse me. All right, so B trees solve a lot of those issues. They are a sparse tree structure, which means that unlike, say, a binary tree, if you've heard of that before, they have many, many children, not just two. And what's kind of neat about them is that they're always balanced. So any path from the root to a leaf node is the same length to any other leaf node. And that makes them pretty useful. It really does. So our discussion last week, I'm not sure how well I covered over it, but this is what we kind of ended up with. The idea is that we have a B tree type, okay, and it's technically indexed by something called an order, or branching factor, if you will, of the tree. This order imposes the rules on how many children and how many keys a node or a leaf can contain. And I think we decided to kind of put it here and here. So we're kind of like just putting it in our record. Could do it at the type level if we wanted to, but I felt like we might just want to try it this way first, see how it goes, kind of thing. And so the B tree nodes, yeah, so you have the root node, which is kind of special. It has a few special rules, which is why we new type wrapped it here. The root of a tree could be actually not just a node. It could be a B tree node. So it could be a leaf or a node, which is what we have here, the sum type. And if it's a leaf, you can have, you know, one or up to order number of keys in it. And if it's a node, well, when we promote it to a node after we fill up the leaf, the special rule with nodes when they're the root node is that it's allowed to have a minimum of 2 keys. is important. Super important. But it can have up to the order number, or the order number of children, or the order -1 of keys, I think is the way it goes. Then you gotta start branching stuff off. So let's try and get this going. I'm gonna take this like nice and slow because I haven't implemented a B+ tree. I've read about them quite a bit. I've watched a few videos on it. I've attempted a few to goes at this on my own time. I think one of the things that are going to make this a little bit tricky to do in Haskell is that these trees tend to grow from the root up. Yeah, from the roots up, from the leaves up. I should say the root because there's no roots. Well, there's a root at the top. Weird. Anyway, welcome, welcome, friend. Let's do this. So let's just start with an empty one. That's a simple thing to define. Technically, we need to give the order of the tree. I don't think we're going to keep this integers because we have some restrictions on the values that could be put in here, and I don't want to have eithers everywhere. I'd rather push the restriction up to the caller. But int is fine for now, just to feel this out. We won't go too far without changing that, hopefully. So the empty node is going to be a B tree, our new type, a root node, a new root node, with a leaf, as a leaf, I think, is how we want to do that. Which we're going to end up with a lot of wrapping. B leaf, because of this nestingness. I don't know if we want to remove that. But let's construct our leaf with the order. The leaf has keys and values, which we can... I'm going to qualify that in a second. Empty. The empty instance of the vector. And nothing, no sibling. I'll import that type here and qualified. Cool. Now catch up with us here, GHCID. You know, the new version came out. I should check that out. We're still on the one prior, but yeah. Not in scope. Oh, maybe it is not actually a thing. Maybe it's just v.empty. My bad. My bad. Sorry, GHCID. You're right. You're right. It's always a good idea to have a healthy relationship with your compiler. Oh, especially in these pandemic days when we don't get out much. Socialize with my GHC compiler. Okay. So we could like create smart constructors for the different parts of these things. Or we could just dive in and go straight for insert. What would the type of that be? A key, a value, we return a new B tree. Now, maybe I'll introduce the invariants on the B+ tree as we go along as an interesting sort of way to, I don't know, maybe I'll just introduce them one at a time, because I find if you give too many definitions up front, sometimes it just overloads your brain. It overloads my brain, and I don't even want to get started. So if you just start a small little piece at a time and make baby steps, maybe we can have it reveal itself to us in time. How to do this. All right, so insert. All right, the first case we're going to have to deal with when we're inserting on a B tree is we're going to have to unwrap that leaf node, because let's say we're going to start with inserting on the empty. So I'll go ahead here. This is going to be layers. layers and layers. Leaf, it's going to be the order, the keys, the values. We'll leave the pointer out of it for now. Let's just put a little underscore there. Little hole. Right. Oh, the key we want to insert, of course, and the value. Thank you, little hole. Yeah, that's what I expected, the B tree. We got to return a B tree. Okay. So if we're just inserting here the key and the value into our leaf, and it's just the empty one, we could just wrap that back up. And then with the same order and everything. And in fact, we might even be able to just ignore that order for now and use just record update syntax to insert our key into the keys and our values into the values. And to do that, I think we just have v.cons takes the value from data.vector, and it doesn't display the documentation there. That's unfortunate. But it takes the value key, and we'll put that into keys, and the value v.cons the value into values. Yeah, well, not initialized, whatever. That's okay, I'm going to leave it partial for now. Let's fire up our REPL and check this out. Rosby server. Right. GHCI, come to me, friend. Yep. Okay. Just a warning, the same warning as we got before. We'll fix that up in time. We're just kind of experimenting here. So, who says you can't write? You have to write a complete program before you can even experiment with your Haskell program, right? Totally partial, totally fine. We want to try to insert empty. We have to give it some kind of order. So let's just say it's 3. I don't know. Let's put B in the key in the tree. We don't have a show instance, of course. So let's add that to here. Reload. There we go. Yes. Oh, no, we got an exception, of course. Okay, fine. That's because I'm not doing things right. Record update syntax uses that guy. You're right again, GHC. See, I'm tired today. Slow and I'm missing it. All right, cool. Dope. All right, so if we insert into our empty tree, it'll put a value into our empty tree. Yeah, it's good. I like it. Okay. So. Now, let's talk about order then. There are laws. The reason why we have the order in the leaf node and in the node, which we'll have to kind of keep track of at the value level and propagate those through as we construct things, But the reason why we have that is because there are a certain number of values and keys we're allowed to hold in a leaf. All right, so if we go to insert a new value into this leaf in our root node, and we go over that limit, we got to do something else here. We can't just fill up that leaf infinitely. Cool, cool. Yeah. So what is that law exactly? Let's just search a little search for b plus 3 thing. See if we can find a page with it. Yeah, something like that. This is our b plus tree. See? Emery tree, all that stuff. Let's jump to the overview. What is the overview? Where's the thing? Maybe it's under characteristics. Or no, maybe it's here. Yeah, so the order or branching factor, right? That's what we're talking about here. Root is the exception. Internal node. So that's our node type. Can have between 4 and 7 if the order is 7. So that's this here. That formula there, if you can see it. Where's my pen is not working. Okay, this guy over here. Okay, you can't. It's kind of hard to see in this font here, but this little, it looks like this. That just means upper bound or top, like join and meet sometimes, depending on what you're looking at. But up here, you can think of it as rounding up. That's the branching factor divided by 2. All right, so whatever the half is. That's where it's getting between 4 and 7. It's allowed to have. Jeez, I wish my... yeah. Okay, so that's cool. Now the root is the exception. It's when it becomes a node, it's allowed to have between 2 and 7. Leaves have no children, they just have values. That's kind of another special thing about B plus trees. Compared to B trees, which is where they come from, the plus is that all the values are pushed down to the leaf nodes at the bottom. So no internal nodes don't have values in them, they just have keys. And the link, we can create a sort of linked list of the leaves at the bottom. So if we happen to want to implement search in our tree, or in our index at some point in our server, we could be able to do that as well. Right, search, so leaf nodes have no children, but they're constrained. So the number of keys must be at least, rounded up, b over 2, and at most b. So they're allowed to have at least up to 7, in the case of 7. So in the situation where the tree is nearly empty, it contains one node, which is the leaf. That's where we're at right now. So it's allowed to have up to at least only as little as 1 key, but at most b minus 1. So it sounds like we need some kind of guard on our insert function there, in this case where we're checking out the leaf node. And searching is kind of like binary search. And, so insertion, this is kind of like the algorithm for it, insertion. So we'll have to have some sort of search function to determine which bucket the new record should go into at some point. If the bucket's not full, We add the record. That's what we did right now. So I guess we kind of have to check if the bucket is full or not. Otherwise, before inserting it, we got to do the split stuff, all this stuff. Cool. So, in that case, let's check. Let's add a guard on here, I guess. So in the case where the order, which I'll have to pull in here, is the length of the vector length of keys. So the number of keys that we have is less than order. Right? And we could say less than and equal order minus 1, but I think this is the same. And then we can do what we just did. And maybe tidy this up a little bit. Yeah, we don't really need to push the order through. We just need it for the guard. Cool. Otherwise, just like in our algorithm description, got to do something here. Hey, Beavish. Hopefully I got that right and didn't butcher it. Beavish. Yeah, it's you. Yeah. I find it's convenient for a lot of reasons. I like you. One, don't tell anybody this. It's kind of a secret. But if you're trying to read an article that has like those fancy JavaScript paywalls, it doesn't have JavaScript in it, and they usually leave the full text in the document. Not all sites do that though. Some sites do server-side rendering and only render so much of the article and make you pay, but it's also good just for reading text stuff. I mean, it can render pictures and whatnot. It's not the greatest browsing experience, but I find it's good enough for technical stuff. And in that way, I don't have to leave Emacs, because why would you want to do that? I don't know. Right. Okay, so the otherwise case is where we kind of get a little more complicated. Okay, so before inserting the new record, so the case where we're at our maximum capacity in our leaf node, I guess we got to split up the leaf and create an internal node, I guess, with the keys in it. Yeah, we're going to create an internal node, the keys in it, that point to the leaf nodes now. And we're going to have, so I guess we're going to end up with some child nodes that go to leaves, and we maintain the values between the two. So this is going to be a little bit tricky. Not too tricky, hopefully, but a little bit. This is just for the leaf case, so it shouldn't be too bad. Okay. Yeah, it is pretty awesome. I like that, you know? Never underestimate old tech. Sometimes it's good for getting around things. Okay. Yeah. So we're gonna have to create with our B node. We're gonna have to create a node of some kind, aren't we? We might need to do some stuff, like maybe have a let here to bind some things. How do we split a leaf? Let's split a leaf. Let's create a little split leaf function. Let's take a leaf node. What's going to return? A node. Seems reasonable, right? Except, what do we got to do? We got to push the values through somewhere, don't we? Right? We got to put them in one of these leaves. So we're getting to the max size of our leaves. Say it's 7. Ugh, my pen. Why? Let's see if I can make this work here. Hang on a second. My Wacom tablet is pretty old and a little fussy sometimes. There we go. That's better. Okay. Yeah. So basically, we've got our leaf here. Right. It's got some values in it. Some keys and some values. Pop, 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 pop. And everything's filled in but b minus 1. So all these blocks up to here. And then we need to turn that into, say this key, I don't know, is like 3, 8, 9, 10, 50. All right, I think what needs to happen here, if I'm not mistaken, is that we're going to split these keys in half. We have an odd number of keys, so it's going to be rounded up. Right, little b divided by 2 thing. So we're going to take these set of keys, and this set of keys, and we're going to split them up. And then what do we got to do? Sorry, my hands are not in the home row, so I can't do this. Hiya, hiya, hiya. Okay. So before inserting the new record, we split the bucket. The original node has that many. The new node has... Okay, so we create a new node. Move the... Oh, see, this is where that kind of gets sketchy, as if you start using Unicode. And insert the new node to the parent. And repeat until the parent is found that need not split. Okay. Let's see if we can find a better visualization for this. Just to shows. Maybe this site will help. Right. Okay, let me just get rid of my cruddy drawing. Okay, so we start with empty, we add 8, we add 9. What is our branching factor here? I guess maybe 2 in this case, or 3. So we add the 8, we add the 9. We go to add 10. We split 9 up into a node. These become leaves. 8 and 10. Go to add 11. So the insertion would go 9. 11 is greater than 9, so we go to the right child. And if we have more, you'll see it as an example progresses. 15, right? We go to insert into 10 between 10 and 11, but we can't, so we got to split that. Push it up to the parent. Becomes the rightmost there. Right, so that's, I guess that's the whole process here. We got 3 in here. So we move the 11 up into the parent. 10 becomes the child, the middle child, and the late child. We had 20. Down. 17. We end up with this situation again. Dunk. And then we have that situation with the parent. Gets too full. So then we got to create a new one. Now we have 2 new internal nodes for that one, so on and so forth. Yeah. And then of course, almost all the example algorithms you'll see are going to be very, very procedural. So let's think about how we'll do that with what we've got so far. All right. So early on, get here, we get here. Go to insert 10, we're good. No, can't. Turn a leaf into a node. Okay. So whatever after the remainder, so we split it in half. I think I see what's going on here. We split it in half. Right. We take these ones, they'll go to the left, and these ones will become our keys in our root, in our node here, I think, maybe. Right, and those guys come down here. These ones go here. And then whatever we insert goes over here. So, like inserting. Woo. Hopefully that's right. We'll probably encode some of these things as property tests, just to make sure that we're implementing this correctly. So we do probably need the key and value we want to insert. So let's pull apart the leaf. Don't know that we need the order at this point when we're splitting the leaf. We'll probably need the keys and the v's. The key that we're inserting and the v we're inserting. Okay, actually we do need the order because we need to figure order is b and we need to figure out b over 2. Okay, so the split happens to be no, sorry, by 2. All right, so I think that's, so if we do that, right? That's not rounding up, it's rounding down. Is there a way to guarantee with Haskell that the memory will be laid out correctly? I don't 100% know. That's kind of what we're going to be experimenting with once we get further into the data store. So my intuition is probably not, but it might be okay. Okay, so ultimately, for like maximum super performance, right, we're going to want to have the storage system, like the way we're storing the user's data in memory at the leaf level of our tree. You know, it has, notice how it could have just pointers into a structure. It would be really super performant if, from what I understand, that we we divvy up that memory in blocks in basically a big sequential blob of memory, and the block we size the blocks to roughly about the cache line size of the machine, and that way when we need to pull in values into memory, like when we're reading them, it's probably about the best thing you can do, right? That way you don't have to overfetch or underfetch and do all those sorts of things. The question is, like, can we do that in Haskell and guarantee that? I don't know. We're going to experiment a little bit and see if we can at least get decent performance, but I don't know that we can lay out memory in Haskell to that fine a grain. We might be able to cache align things, and I'm hoping that at least at the value layer, we'll be able to maybe serialize things in such a way that maybe we'll be able to get those cache line boundaries. And one of the things I'm thinking we might need to avoid at some point is allocating onto the Haskell heap, because the garbage collector is going to be visiting those objects on the heap constantly, which is going to be a bit of a performance thing as well. So there is a way to protect against that issue with compact regions in GHC. How well that's going to work out, I don't exactly know how that's going to happen. We're just going to have to try and play around with it. It sounds like some of the limitations on compact regions is probably going to kick our butts. If I'm not mistaken, they have to be immutable structures in there, and I don't know that byte strings are going to be cool in compact regions. Nevertheless, it's worth trying and experimenting, because even if we fail, we'll learn something interesting, and we'll learn a lot about Haskell's memory structure and how it structures memory on the heap, and how the garbage collector works, and all this kind of stuff, which is going to be super fun. So if we really want to eke out that level of performance, we might have to go to C to get that, which is what I was originally going to try and do. But some friends of mine were like, well, maybe we should try to Haskell anyway. I was like, okay, well, why not? Right? This is a project for learning. I don't think we're going to make a key value data store that's going to compete with some of the more popular key value data stores that are kind of already out there. I don't really have any super innovative ideas around key value databases. It's not my specialty, but maybe it will be as we build this. Who knows? I always liked databases, and as a user of databases, I often find that I have to, at a certain point, understand a fair bit about their internals in order to eke out the maximum amount of performance for applications that use them. And I've always really liked doing that. So why not build databases? And why not Haskell too? Right, so we got the split size. That div operation rounds down. So there's got to be a better way to do that in the Haskellage. Right, that's not slash slash, what am I doing? 1.5, okay, that's obviously going to be a fractional, and I need a function to round up. It's probably called round. I don't know. I just don't know if it's in Prelude or not, so I'm just going to Google it. Like non-B maybe? No, that's not the right type. It's going to be like integral. Round. Is there a round up? Round 2. Round up. Nothing that we're going to have to import libraries for. Ugh. I wish I remember the name of it. Upper bound fractional. Ugh, no. I'm getting into the weeds here. Oh, let's see. What's a hacky way we could do that? Alright, so we round 3 divided by 2. That's what we want, but 4 should still be 2, 5 should be 3. No, it's going to 2. Dang. We do something super hacky. Oh, not always guaranteed to be stable. Probably not the best. What other way could we do that? We could do it by, well, we take 5 divided by 2, which is 2. The remainder of that would be, from the original B, would be 3, and that's what we want to split at. Alright, so if our branching factor is what we want, and if our branching factor is 3, we should still get 2. Nope. Yeah. I don't know if I like that. I hope there was like a round up in base for some reason. Round 2. It's round to float, right? I don't know. What ifs? No, we do have that. This is totally janky, but let's just do it for now. It's the jankiest. Okay, so we got the split for the leaf. So that's going to tell us all the things that we want to take to the left hand of the child. I think, you know what I think it is? We're going to split everything less than this down. What we're going to take is the key. And that will be, I don't know, left keys will be something from the keys. We'll have left values. And we'll have a new node that we got to construct, and possibly a new leaf that we need to insert a value into. So one of these. Is that enough? P-tree, the node is going to have the same order, and it's going to need potentially some keys and some children, which are going to be left, which will be a leaf with the same order. This is probably where we're going to be propagating the order around a fair bit. Probably left keys, whatever that ends up being, left values. We're going to have to tie the knot on this here. Because that's going to have to point to the next child, the next leaves in this node. Next leaf in this node. And on the right leaf that we construct can have nothing. It's got the same order. I'm not sure what we're going to put in there yet. That could be nothing. Yeah? Okay. I mean, that's looking pretty reasonable. So we just got to figure out what's got to be left keys, what the value is going to be for left values. That's got to be tied to our vector. So we're going to have to, get a subset of our vector, the original vector. And don't need to index subvector. a slice. Without copying. Okay. Oh, split up. Look at that. Unsafe slice. All right. Ooh. Ooh, unsafe. Okay, split at. Yeah. Actually, that might be perfectly what we need. Right there. Split that. Left keys, right keys? Question mark? Keys? Left values, right values? Question mark? We'll do that again. These, yeah. Okay. So let's see, left, now we have a hole there, the tie, which we need to tie into right. That'll be just right. I like how that sounds. Be just right. Just right. That's perfect. All right, and then we just have to figure out what the values need to be in right and what the values need to be in the node. Well, we know what the children are going to be, but what the keys in node would be. If there are any keys in there that we should put, perhaps. It's got to put keys and children. So I think the children... children, I think is a vector. Yeah. Constructing one. Not that. $, please. Left and right. Slowly filling it in. And this is often how I approach a lot of my Haskell programming. It's like I fill in the parts that I know and the rough structure of what I'm trying to make. And I just sort of leave out the things I'm like, I don't know how to do that yet. And then, yeah, just kind of fill it in as I go. And sometimes I'll write in an equation that I'm like, this should exist. I just haven't thought of how to implement it yet. And then fill it in later. And once I get the compiler errors gone, oftentimes things just work. How do you do it? I've been really enjoying the streams that have been showing up lately. A lot of other Haskell programmers have picked up the mantle of starting their own streams and doing their own Haskell live coding and stuff, and it's been pretty awesome. So if you're a Haskell programmer and you're thinking about it, or you're just starting out even, don't be shy. It's cool. I think just people seeing other people programming in Haskell is a good thing for the community. Because a lot of times people talk about what it's like to program in Haskell on the internets, you know. But seeing people do it, it's a good thing. That's a good thing. Okay, so on the right side is what I'm kind of like, I don't know what I should put there, and I don't know what I should put in for the keys of the node. We still have a value to insert. Given up here. So we haven't used this K, we haven't used this V yet. We've used Ks, we've used Vs to generate new values. So it's got to be something, we got to do something with that. Do we have to like recursively insert those values, maybe? let's check our insertion example here, and maybe check our example algorithm. It's this step here that I'm kind of curious about. So we can imagine this being our leaf with 8, 9 in it. We go to add 10. It's taking the rightmost, right? It's just taking the 9 in this one example. And then inserting 10 into the leaf as the value there. But what I'm curious is if we're splitting, if our branching factor is a bit bigger than this, right? Do we take that whole thing up, or do you take one key up? You know what I mean? Let's check this. This is really hard to read. I don't know if I can. Oh, there's a huge delay. Oh, sorry. Maybe I should switch servers. I don't know how to do that though, but I heard there's a thing you can do. So by it, you mean streaming. Yeah, maybe. This code here is terrible. What even language is this? Well, we're scrutinizing if this is a leaf, so maybe that's where we're at. Yeah. It's hurting my brain. So much mutation. So many variables. So poorly written out. Geeks for Geeks, not always the best source, but sometimes okay. Pseudocode. So if y is full, I'm guessing y is our leaf, then we split it. Change x to point to one of the two parts of y. If k is smaller than mid key in y, then set x as the first part of y. So I guess k is the key we're trying to insert. So we need an ORD instance on our k. If it's smaller than mid key in y, well, I guess the middle value. Okay. Then we set x as the first part of y, L second part of y. We split y, we move the key from y to its parent, x. Goodness gracious. Yeah. So this is what I mean. It's sometimes not the greatest writing on here. That's okay. So what I think it is saying, though, is that when we go to split the leaf, if it's full, we first got to check if the key we're trying to insert is less than the value at the midpoint of keys in the leaf we're splitting. And if it is, then I guess we make the midpoint key in the parent node. And we insert it on the left. Else we put it on the right. I guess that kind of makes sense. Right? So let's draw that out just quickly so I think I understand. All right, so what we're going to do, let's say our branching factor, I don't know, is 5. All right, we got 0th, 1, 2, 3, 4, and 5. All right. Our 5 over 2 is going to be 3. Right. So we're going to check, we're going to scrutinize this value here for the key we're inserting. So say we're trying to insert, say we got like 8, 11, 13, 14, 16, 20. And we're trying to insert 10. So k is 10. That means we're going to check if k is greater than or less than 14 or equal to. If it's less than, I guess what we want to end up with, we'll make 14 a key in our node. So let's maybe use a different color for nodes so we know it's a node. All right, we'll make that a node, and then we'll make 2 leaves. All right, and we'll insert 10 on this side. 8, 10, 11, 13. And then we end up with 14, 16, 20 over here. And that's because in our B plus tree as well, like our nodes can't have values, so they get copied down to their children. So this 14 will end up down here. So this will be our left, which will tie into this one here, that equation there. This will be our right, to tie into this equation here. I'll have to tie the knot on this because this needs a pointer. That one. And yeah. Okay, so what we're missing from here then is the split, hopefully. We're missing just the discrimination on the middle value, and so which side we should insert the new key on. So the k, we need to investigate k. And the value that we split at on here in the original keys. Now we need to make sure this key that we pull up into the node is going to be in right. And then Bob's your uncle, I think. Yeah, so let's do that. Pachow, 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 pachow. Okay. So let's just put this off to the side for now. So we go in here, we're gonna have to investigate, we're saying k at the midpoint or split point in keys. So we can index, do that with an index on vector. I think it's like that. I think we go the index first. Double check that. So if that does equal it, so we have to use k. It's less than that number. Then we do something. Else we do something else. Probably make that a value, but we'll see. Okay, so if the k is less than that, we said that the left, we're going to insert onto the left leaf. Well, something happened here with my sound set up. Hang on a second, just making sure we're still live. Yep, good, good. Okay, never mind. Yeah, so sorry. Distracted. Do left, right. Left keys. Yeah, left keys is what we want to change on that when we investigate it. So, what if we could put that in regard? So what we would do here, what I want to do, but this isn't right, is we would put it in there, but we have to maintain the sorting order. Right, because we don't want to put it anywhere, otherwise binary search on the keys doesn't work. So hacky grossness would be like, you know, consing the value in onto the left keys and then sorting it. If there is such a thing, but we'll need for sure an ORed instance. And maybe even, I don't know if we'll need an ORed on B. We haven't really discussed that yet. So that would be like what left key primes would be. Right keys would still be its own thing. Is there? No, I don't know if there's a way for us to use guards here and still keep this split value around. That would be cool. Yeah, and then right keys. So I want to do something here. So just rejigger this a little bit. See if this works a little better. We'll put this at the top level. Split of keys. And something else, something. where the split some x's is the thing, the midpoint. Because we still need to investigate that. I'll just double check the index function that I'm doing that right for at least. Yeah, it takes the int. Okay, the int index first. So I'll flip these around. Midpoint. Okays. And length of some x's is we actually need to give the order, don't we? Because at least on the leaf, I don't think we do, because the leaf could be up to B. But we do have to split earlier, so order keys. So this will be that formula here. Pop, pop, pop. 3 over 2, it would be order divided by 2. Okay. So if the key is less than the value at the midpoint, we're going to do something. What are we going to do? We're going to get the left keys. And then we got to insert the value on the left side in the correct place. We even like to do it like this. K into left keys. And then we can make the left and the right, I think. This equation still makes sense. Except we'll make that left keys prime. Left values. Ooh. Janky. We also have to insert that as well. At the same index, we inserted K into... Tie that out to the right. That will also be, I think, the same equation as well. Ish. Except now I think we have a little bit more information about what goes in here. Right keys, at least, would go in here. And potentially right values. So let's bring that down as well. Okay, and that would go here. Right values. Thing. And then we can construct, I think we have everything filled in to construct a node. Okay, so that would be B tree, the B node. Oh, wait, we have to make sure also just a reminder. So when we're constructing the node, some key has to go in there that we're splitting from. Right, so the grows from the parent, from the leaves up. Right, so one of the values in the leaf has to get promoted to a key in the node that we're splitting to. So we still have to figure that part out. We can construct the order, but the keys are going to be kind of and the children are going to be as we had before, I think left and right here. Okay. It's getting a little hairy. Okay, so inserting to the left values. We have to define insert into still. And we also need to handle, or sorry, into the keys and the values. So, and we have to insert them the same the same index, I guess, is kind of the idea with that here. Right, so the idea of the keys and values is that these vectors one-to-one, that's probably another invariant we'll have to maintain internally just for the way we're representing this. They should be the same. The indexes should relate to one another. Good to note, just in case. Okay. So how do we do that? We could have a function that returns a tuple. And insert into would take the key, the V, left keys, and the left values, and return that tuple. It returns into something. So this becomes left values prime, assuming insert into works. It does what we want it to do. That means what we think it means, and then that means we just have to remember the X node key. What happens with the value? I think basically what happens is this discrimination here is how we're going to split on the value at that midpoint is what's going to get promoted. And when we get the right, when we split into right keys, I just want to make sure that that value is there. It might be in left keys. Let's just double check how that works at the REPL actually. So let's say we had a list of 5 numbers, because our branching factor is 5. Oh, we don't have V, of course. Import qualified. Data vector as V. Try that again. Okay, so we get the splits like this, where the value that we're splitting at 3, so that's like 0, 1, 3. Oh, it is showing up on the right side. That's good. That's what we want. So we don't have to do anything special here. And hopefully we just have to make this, if this function's right, then all our invariants on the leaf nodes and the node itself will be maintained. It will, I think, in the case where the root node. The root node's allowed to have a node that only has 2 elements. But an internal node, a regular node, can't have that. It has to have at least be divided by 2 elements. And up to B elements as children. And then B over 2 minus 1, and then B minus 1 keys. So this, I think, this equation I think is only going to work in the case where this is the root. At the root. We're only really going to, I was only really going to use it at the root actually in this otherwise case over here. Right. Yes. You want. Ugh, that's what I hate about import qualified. Importing operators. And you don't take. Oh, I got that wrong. I guess it's supposed to be the vector first and the int second. Yeah, sorry, I gotta flip it around. Dirt. Right. Right, because it doesn't want to, well, leaves, of course. Leaf. To wrap those up. And then, okay. let's not wrap those up until we construct it because of tying the knot here. Okay, cool. Oops. I don't know. Let's just put K's in there. Just no. Did I get something weird there? Node KV, yeah. Node order keys children. And B node is our constructor. Yeah, that should be B tree. Could expect the actual type node KV with the actual type B tree expression. Oh, of course, it's expecting a node. We don't need to wrap it up in the B tree here. My bad. Okay, midpoint needs to be an int. Oh, what is it? From integral. Right, midpoint returns an int. Why are you upset? The vector of k's. Sorry, I'm starting to drift off. You know, that's how it is. Let me just take a sip of water and take a step back for a second. There's some other stuff I want to get to as well, other than this, but that's. I was talking to someone who was interested in contributing to our database, and I think, well, we got to get this project set up to accept contributors as well, right? So if you're interested in learning Haskell, maybe you're just starting out and you want kind of like a project to actually work on, there's still lots to do in Rosby, and I would be happy to see pull requests come in from you, and you know, do a little code review on the stream. Don't be shy. You know, there's plenty to do, and accepting pull requests is part of the job, and reviewing code is part of the job. So it's all good. So we should probably set that up before we finish here. Yeah, so it's looking for a real fractional int arising from the use of midpoint in the context of this. Because I'm doing something synecdoche. What does it think midpoint is? Turning a numeric C takes a real fractional A. Oh, okay. Is int part of real frac? Maybe not. Maybe that's the problem that's trying to tell me about. Real int. Bounded int, integral int. Yeah. That might be what the type error is, right? That seems right. Could not deduce real frac for int. Arising from the use of midpoint. Because we look at the type of midpoint. Or what GHC thinks infers it to be. A has to be an instance of real frac. Because I'm a moron. And I'm dividing it by 2. That deduces that to be real frac. And when I was doing it at GHCI, it's kind of being nice to me, I guess. So, is there a function to go from real frac to numeric, maybe? Ooh, there it is. That's what I wanted. Ceiling. Couldn't remember the name of it for the life of me. And we just discovered it, friends. It is ceiling. Ceiling is what we want. Okay, but we're still going to have a problem with real frac, but at least we can fix that equation. Oi, oi, adding 0.1. At least we can get rid of this. Ew, fix me. That was so gross. I felt so dirty. So it's not round, it's ceiling. My mic disconnected. Okay. Lets me testing, test. Or maybe it's just not picking me up. Thanks for pointing that out. Sorry about that. Can you hear me? Is that better? Doobie-doo. Let me know. Let me know. Right, so ceiling is the function we want. I don't know how on earth I forgot that earlier. Big apologies for that. Just checking my mic levels. Hopefully we're still good. And so that's good, but we might still, do we still have a problem with fractional, real fractional? Yeah. Yeah, we do. So do we have something that goes from some numeric A to real frac B? Okay, maybe not. Let's look that up. I don't think there's supposed to be spaces in there. I don't know. I don't make this stuff up. Or maybe I do. Maybe I only have it like this. Yeah, there you go. No check marks. Whatever. Cool. I think that's pretty good requirements-wise. This could probably be broken down into smaller tasks, but it's a pretty cool project. So there you go. If you want to contribute to Rosby development, that would be a nice task to work on. If you're already working on this, cheers. Looking forward to checking it out. What else should there be? Well, that would be nice. What else is there that we were doing? We got the logging kind of working better. We have this to do. What's this to do here? Ah, yes. Should probably have an issue for that. So let's create a new issue for that. Yeah, server responses. So what's the problem here? We're just doing the response okay, whether it passed or failed. And I don't know that we're in quite the place yet, code-wise, where we could actually do anything about this yet until we have a store. And that store could tell us whether it's okay or not. So this is not it wouldn't be a very good issue for now to have, but it would be kind of cool to. What could we do here? We could probably. We could probably fake it. Because we might want, actually, yeah, we might not want a response okay. There might also be the chance of having a response not okay. Ugh, jump to definition still doesn't quite work. It might because we're sort of doing it this way. But if we go to the protocol and we look at the response, I don't recall if we actually implemented the fail one. Okay, we have a fail one. It can fail. Yeah, so I guess to get the client working, it might be useful to at least be able to serialize the fails sometimes. Yeah. So let's make that the issue. Let's yeah, I don't know if we can work on that just yet, actually. Okay, so client is a good idea. We fixed the logging already-ish, and we're working on the storage backend. We need documentation. Not yet, though, because it's still pretty early in the project. All right, well, we're running out of time here, so that'll be good enough for now. Add a REPL to the client if we can. If you can think of something else, I implore you to add an issue here. Even if you think it's something I should work on, maybe on the stream, we can kind of create this as like a little backlog. And tell me what you think would be interesting to work on next, and see on the stream, and maybe that could be a kind of little interesting way to make this a little more interactive. So we got an issue backlog now. probably, update the README a little bit would be nice. Maybe that'll be a nice one. Update README. Project, goals, etc. That's a really low-hanging fruit, easy one. Maybe we can create a little label for it too. Documentation. Super. And we're also going to need, just project-wise, if we're going to start accepting contributions, a contributors guideline. I don't think it necessarily needs to be fairly strict or anything, but just having a few guidelines in there would be nice, just so that newcomers can kind of get a feel for what we sort of expect. No. We can get from integral. We got real to frac. And from integral. Not quite, friends, not quite. So we maybe if we turn it into an integral first, that would help. Do we have that? I think we have that. Yeah. Cool. We do. Thanks, GHC. So that fixes that. Okay, cool. Yeah. So our node keys is the only thing we're not super sure what that should be. Should all the values from the leaf that we're splitting, like to the right, become the node keys? You know what I mean? Or just one, and then the rest become a new leaf on the right side. We could just kind of assume that we could take the head of right if it's not empty. But if it is empty, that's another other case we would have as well. Yeah. Okay, we're running out of time. I do want to do some other setup stuff for the project, so I'm going to put a pause on this one for now. Let me just check with chat here. Friends, how's it going? Oh, did I get disconnected? I hope I didn't get disconnected. That's going to be really annoying for exporting the videos. Okay, cool. Yeah, so I want to put a pin on that right now for now. We'll stash that. Let's stash that. Let's put on a branch. And then I'll push out the work branch so it's like kind of a work in progress and we can keep a peek at that going. If other people, you know, create a branch, starting at master, B-tree insert. Okay, cool. So we modified B-tree store. Add the empty constructor and the beginnings of the insert function. That was a work in progress commit. Cool. So I'll push that up. And then let's just take a gander over at the project and start putting together some tasks and low-hanging things that we could get other people working on, so that if people feel like contributing to Rosby and they're looking for something to contribute to, go ahead. It's a learning project and it's totally open. I'm totally open for doing that. Cool. So GitHub, we'll just use the GitHub issue manager for it. Okay, cool. So, I don't know. I've never really used the project board stuff. Anybody else use this? Seems like a lot. However, let's think about all the things that still need to get done, because there's a lot. We're in the middle of working on the store, the B-tree backend. There's still some stuff on the server that would be nice to have. So, what are we missing here? I think on the server side, for starting out the server, the configurations, is that looking okay? Server source. We have the configs. Right, this library does sort of do that already for us, doesn't it? That's why we used it. So don't need that. Oh, it'd be nice to have a CLI for, or like a little REPL for the client. An optional REPL, that would be cool. Developers' interest in server could test stuff with. So high-level ideas for the REPL client would, I guess, kind of look a lot like, I'm thinking of similar to the Redis CLI client. Dang, my internet's so bad today. I don't know what's going on, but I just dropped again. So if this gets broken up, I have to re-edit everything and manually, I guess, and upload it to YouTube. So sorry. Hopefully that's not happening on Twitch. What a pain in the butt. Okay. Ugh. That's what I got. My connection's bubbling out, so I'm gonna have to like call it here, friends. Thanks for coming by, watching me stream in live code. We added a few issues to our backlog. So again, if you're still watching and you can see me right now, add some tasks in here if you want me to work on something in particular in the future for a future stream. And if you're looking to contribute to Rosby and get involved, pick something up in here and let's get going. I'll check out it at the beginning of the stream and we'll check out the issues and if there's any open PRs and stuff. And, we'll review things and manage the project as we go along and make that part of the stream too. If that's becomes something. I don't know how that's going to go. So yeah, thanks again. It was nice hanging out with you, and may your monads be free and your types always check. Take it easy, friend.